Good morning, students. Can you hear me?
Good morning, ma'am.
I'm audible. Okay,
Morning,
okay, okay. Thank you.
ma'am. Yes, ma'am.
Oh, sorry, I was speaking without unmuting that. Yes. Now I'm audible, right?
Yes, ma'am.
Yes. So today, are you aware that you have two chemistry sessions? Now one and one more at 3:30 to 5 o'clock? Yes, you're aware about that. Fine. Fine. Okay. Yes. So, mm, tell me something about what should I ask? There's so many things. Yeah. How is borazine or borazole or inorganic benzene prepared? We'll wait for a couple of more minutes so that a few more can join. And meanwhile, you'll utilize your time. I'll ask you questions. You want to answer anything, you can raise up your hands. So when you have, is it boric acid, Fezan? Think. It's diborane. It's diborane and ammonia in the 1:2 ratio. Low temperature or high temperature? That who is going to help me? Very good. Very good. So it's diborane is to ammonia into 1:2 ratio at high temperature. Same diborane and ammonia, but with excess of ammonia and high temperature. Very good, Ayushi. You can't see the screen. Um, can you just see group 14 written, Arshia? I not written anything or not. That, this is the first slide. Now can you see? It's blank. Now, okay. No, no, I didn't click. I didn't put the click. Next click where all these elements will come. Fine. Okay. Okay. Yes. So, yes, as I was telling you, you have diborane plus excess of ammonia and high temperature. Why take the pains of typing so much? You can tell me orally. You don't see now how much your teacher speaks. Huh. Diborane with excess of ammonia and high temperature. What do we get? I repeat, diborane with excess of ammonia, high temperature. Anyone? Very good. Boron
Inorganic
nitride or
process.
inorganic graphite. Yes. Inorganic graphite. Fine. And then what is left? Diborane with excess of ammonia but at low temperature. Yes. BH2NH3 whole twice overall plus BH4 minus or in
Four.
simple sense B2H6.2NH3. Very good. Yes. Very good. Good answering, good participation. And since it's time, let's start. Let's continue. Let's utilize this class to proceed little more in our syllabus. Yes. As you can see, we are talking about which family? Carbon family. Carbon, silicon, germanium, tin, lead, and flerovium. Flerovium. Even I, for the last element, I generally use the IUPAC name. Okay, chalo, tell me one IUPAC name. Say, for example, I have 115. What's the IUPAC name of this? Very good.
Unpentium.
Un pent plus IUM directly. I'll write un and pentium. Very good. Very good. U,
U
capital U for
P.
this, and another small u and P. Very good. Anyway, that's what I use. Easy to remember rather than these names, the latest element. Other names you and all I remember we remember very well. The first element, I mean carbon, yes. Needless to say, the general electronic configuration is Ns2np2. Carbon is a non-metal, silicon germanium metalloid, tin lead, and then flerovi, little scared to pronounce it, that's it, is a metal. Yes. So do we see inert pair effect here? That's what I was discussing towards then and then decided, yes, let's leave it to the
Nothing.
next class. Yes. So it's lead which shows inert pair effect, as a result of which the plus 2 oxidation state in lead. So Pb plus 2
Is more
is
stable.
is more stable than, yes,
Pb plus 4.
Pb plus 4 due to
Inert pair.
inert pair effect. I got a few questions, but seeing the syllabus, so many things there. Towards the end, little bit we can devote, but right now we should concentrate in completing this for our own betterment, for better more time for revision, right? Yes. Coming to the melting points, do you know a particular metal which has very low melting point here? Everything again, the melting point reason is the way it is arranged in its lattice. If it's very compact arrangement, we require more energy to break the bonds, and hence the melting point should be high. Very good, Faizan. Yes, it's tin which has very low melting point here. So otherwise it follows a normal trend, but except the fact that tin will have a lower melting point than lead, and hence the exchange. Yesterday's discussion, ionization energy trends, decreasing order for group 13 elements or boron family. Who is going to help me in case I would have forgotten? Tell me. We start with boron.
Boron.
Boron. One thing I told. Yes, tell me next.
Tellurium.
Very good. Boron, tellurium,
Gallium. Aluminium.
aluminium, gallium or gallium aluminium. Think.
Gallium. Aluminium. Indium.
Perfect. Because out of aluminium and gallium, due to its transition configuration, is smaller.
Perfect.
Smaller, so its ionization energy should be higher. So after boron, tellurium, gallium, aluminium, and last
Indium.
is
Indium.
indium. No, Faizan, it's absolutely okay. Getting confused is obvious. There are so much of fact-based things. Yesterday I did, so I also remember. Otherwise, I might have also. I repeat then. That's the reason I'll keep on repeating so that gets registered in your mind. What did we say? Boron, tellurium, gallium, aluminium, indium. Fine, very good. So here, carbon. This is easy. Carbon, silicon, germanium, lead, tin. Anyone remembers the melting point order there?
Boron. Aluminium.
Hmm.
Thallium.
Thallium.
Indium. Gallium.
Last, gallium. Good. Who is this Atika? Answering very well. Very good. I did I pronounce your name right? Yes. I hope so.
Some is correct.
It's correct. Fine. Complex formation tendencies. Students, you'll find this thing in D block elements also. So, what are the factors which affect complex formation? Certain times this questions is also asked in boards, Why do D block elements form complexes easily? What you need is vacant d orbitals, small size of the atom. The main criteria is the ability of the element to exhibit variable oxidation states, presence of vacant d orbitals. Vacancy, yes, vacancy of the d orbitals, and that's the reason the ability of the element to show variable oxidation states. Yes, carbon, you cannot think of that. You belong to the second period and you don't have any d orbital. So carbon, you do not have any d orbital and hence no chance. In other cases, small size, high charge, availability of vacant orbitals of appropriate energy are the necessary conditions for complex formation. Yes. So carbon can't, but silicon says, see, this is the advantage I have. And a small brief recollection. This is 1 second. Ha. So this is what I always do. This is like my style. To little bit help students and now less because of the vigorous portion, the rigorous amount, the syllabus, huge syllabus left. Otherwise, I generally do whatever we discussed last, a little bits by bits, pieces and pieces. I help you people recollect for better correlation. So here I hope you can correlate that no back bonding is possible because carbon says I don't have any place to accommodate your electron nitrogen. So here no back bonding. On the yes, could you recollect? And please comment on the hybridization of this nitrogen, students. I know you know, I know you remember all these, but it's my responsibility as a teacher to help you. Yes. What about here? Because silicon says, yeah, I can accommodate. Very good. So back bonding is possible here. This means. Great. I already got the feedback from the last teacher that these students are very, very good. You will really enjoy. I'm really enjoying. Yes. Yes. So students, the same similar reasons, the silicon has vacant d orbitals to accommodate electrons from this fluoride ion and hence can show complex forming ability. Allotropy. Tell me which are the allotropes which are important for your examination viewpoint. Diamond,
Fullerene, diamond.
graphite, fullerene. Fine. Agreed. So, the crystalline allotropes of carbon are diamond, graphite, fullerene. Fullerene just looks like your football and hence it's known as buckyball. We'll come to it. But very quickly, if anyone can just correlate regarding the hybridization of carbon and diamond
sp3.
in graphite, good, good, and in fullerene,
sp2.
very good. People are having a very good preparation. One day, I don't know, whenever, let's first complete. I just want to ask in general some questions based on like either some syllabus which I taught or maybe the entire syllabus, just to check your good grasp. I am already getting an idea, but still, yeah. By the way, the amorphous allotropes are coal, carbon in the form of lampblack, charcoal, coke, diamond. Each carbon is bonded with the four other carbon atoms by means of sigma bonds, very strong, no free electron. Definitely, you can see 1, 2, 3, 4. SP Buckminster full, yes, yes, yes. Fullerene and Buckminster fullerene is basically the same thing. It's my way out to leave that Buckminster. Yes, after the name of the person who must have found it out. Yes, that's the same thing. Buckminster fullerene is the full name, but I just restricted myself to fullerene. Yes, yes. Vaidehi. Okay. So each carbon is bonded with four other carbon atoms via sigma bonds. So of course it's sp3 hybridized. Tetrahedral geometry. Insulator. No free electrons. Hard, extremely hard, very strong, extensive three-dimensional network of sigma bonds. And you of course knows sigma is much stronger than a pi bond. Density, it's so many atoms present in a very small region. Now announce that each person is going to get two 500 rupee note, just like nothing. In a particular place, you announce in the front place of the main gate here. You see the crowd. So many people accommodated in a very small place. What an example I give. So mass, more mass in a small volume. Exactly. Because of this extensive three-dimensional network that's having a high density means a lot of atoms concentrated in a very small region. And because of this very strong bonding between them, you really need to supply a lot of energy to break the bonds between them so that it gets converted into the liquid state. Very difficult. It is having a very high melting point. And the bond length, this is basically the bond length of a normal carbon single bond, and all single bonds are involved. So CC bond length is 1.54 angstrom. Kinetically, the most stable allotrope. Not going more into this because of a lot of time constraints. I have to complete still a lot of stuffs in inorganic. You must be knowing from your thermodynamics chapter that thermodynamically the most stable allotrope of carbon is
Graphite.
graphite. It is
Yes.
graphite. And the
Graphite.
yeah, it's graphite, no doubt. Because the delta G of graphite should be then more negative than the delta G of diamond. Very good. Graphite. We say no. We talk of the
Very.
devil and the devil comes. Yes, no. Yes, the next thing is graphite. Yes. Where each carbon is bonded to three other carbons by means of normal covalent bonds. Hence, the carbon is sp2 hybridized. But what happens is the fourth electron, which is not participating in what? Hybridization. The fourth electron, which is not participating in hybridization, what is it doing? That fourth electron is
Free.
sometimes happens
Conductor.
with me. I don't have a class, but I'm there in the campus, or somewhere you find me. Sometimes after my class preparation, you find me in the first floor, ground floor, somewhere roaming here and there, but not leaving the campus. The electron does the same thing. It is there within the molecule, delocalized, but not in a particular place. Yes, so that the fourth electron is delocalized, doesn't leave the molecule, is there but not in a fixed place. That's what is the fourth electron doing. And see, can you see these dotted lines? So weak van der Waals forces holds the different layers together. So the different layers in graphite are held by weak van der Waals forces, as a result of which these layers can slide over each other, making graphite soft and slippery. The presence of that delocalized electron, okay, the presence of the delocalized electron makes it a good conductor of electricity. Now, graphite is a non-metal, which is a good conductor of electricity, right? Generally, metals are good conductor of electricity due to the presence of free electrons, which are responsible for the conduction. But here, due to this particular arrangement, yes, everyone knows it's a non-metal, which is a good conductor of electricity. The carbon is sp2 hybridized. The fourth layer electron is delocalized and contributing to the good conductivity of graphite. You can clearly see a hexagonal layer-like structure in graphite, and now compare it with inorganic graphite, boron nitride, but also like this, no? Bn, Bn, Bn. Yes. And who will draw so much right now? So on. Yes. Etc. etc. Huh? I'm not drawing it properly. Done. Delocalized electrons make it conducting. The different layers can slide over each other because they are held by weak van der Waals forces. So graphite is lot soft as well as slippery. It's definitely less dense than diamond, and definitely the bond is not that strong as in diamond. So compared to that, the melting point will also be less. Bond length, bond length will be definitely, now it depends upon what bond length are they talking about. Okay, they're talking about the CC bond length. Definitely it is sp2 hybridized, not sp3. The bond length, and so which means the bond has some double bond character. The bond length lies in between a single and a double bond, and this bond length value indicates the same. No, the values, etc., I don't suggest you to remember this. Fine. Thermodynamically, as you people mentioned, based on the value of delta G, gives free energy of formation. It's more negative than that of diamond, as you've already studied in the thermodynamics chapter. Fullerene, just remember football, where you have hexagonal as well as pentagonal rings. So nice it looks, right? Named after the scientist Buckminster, so it's known as Buckminster fullerene. Yes. If you count the number of carbon atoms, the most common one is C60. Maybe I know more about it. So you have C60 as well as C70, the common forms of fullerene, which is also known as Buckminster fullerene. C60, if I'm not wrong, C60 is known as mainly Buckminster fullerene. As I was telling, C60 is also known as buckyball or Buckminster fullerene, name, maybe after the name of the person who took so much of pains to find it out. Yes, students, certain information like this, try to keep it in your mind. Means 32 rings, 26 membered, 32, split it into 20 plus 12. 20, the more one, more membered ring. Think like this: 32, split it into 20 plus 12. 20, 6 membered ring, remaining 12, 5 membered rings. Remember it to be on the safer side. Yes. So each carbon is bonded with the other carbons by 3 sigma bonds. And the fourth electron, just like graphite, must be delocalized. And resonance must be possible between that delocalized electron in conjugation with the other groups. I'll ask you something about resonance. Huh? So many times resonance is coming. Wait, let me ask you after this. So it's aromatic in nature and sp2 hybridized. What is Huckel's rule? Who will quickly tell me about Huckel's rule?
4n plus 2 pi
So
electron.
yeah, out of lot of criteria for resonance, I'm sorry, aromaticity, the molecule must be cyclic, planar. There should be 4n plus 2 pi electrons present. And yes, Ehina. So lovely name, Ehina. So yes, cyclic, planar. There should be 4n plus 2 pi electrons present, which must be in conjugation. There must be a conjugation throughout the ring, right? Even if there is 4n plus 2 pi electrons present, but the system lacks conjugation, then it won't be true, right? Yes. Good. Good answering. Yes. Chats. I'm simultaneously going through the chats also. Yes. Very important. I had recently in another batch, not here, framed a question, which is the thermodynamically most stable allotrope of carbon and the purest allotrope of carbon. The answers are respectively, and then 4 options. Thermodynamically most stable is graphite, and the purity wise, fullerene is the purest allotrope of carbon. Students, what happens now, as I was reading about diamond and graphite, sometimes no, certain other impurities also get bonded with carbon, but that's not seen in the case of fullerene. So just remember, fullerene is yes, Vaideshri. Thermodynamically most stable is graphite, followed by purest form or the purest allotrope of carbon is fullerene. Remember this. Okay, we know this. Graphite is used in lead pencil, plumbago. Aqueous solution of graphite is aqua dag, used as dry lubricants. Hardest allotrope. Didn't ask also, expecting you to know it's diamond. Softest is, in case, the softest one, lamp black. Hardest, diamond. A few things you can remember here in class itself. Don't worry. So, softest, lamp black. Hardest, diamond. Yes. So, now reaction with oxygen. Students, just think about carbon. No, it can form two types of oxides: monoxide,
Dioxide.
dioxide. Similarly, yes, I would like to know one thing here. The nature of CO means acidic, basic, neutral in that sense.
Neutral.
Neutral, agreed. What about this SiO? Do you know that it exists only at high temperature? This SiO exists, as per the data which I read, exists only at very high temperature. This one, not only this one. Let's put a line and all the three. What? What is the nature?
Acidic.
Very good. These three are acidic in nature, and these two,
Basic.
I'm searching
Amphoteric.
something else. They are. Very
Amphoteric.
good. I saw the chats. I saw it now. By the way, these two are
Also amphoteric.
again amphoteric, while GeO is
Acidic.
acidic. So we don't deal with more of GeO and
Acidic.
SiO, as I learned. Yes, acidic. Even this is first one is neutral. SiO is also supposed to be non-metal oxide, should be acidic, no doubt, but it exists only at high temperature. Fine. Carbon monoxide's preparation. Take limited amount of oxygen, burn coal or coke or carbon, you get carbon monoxide. And you people are preparing for medical means you must be knowing that when carbon monoxide combines with the hemoglobin of the blood, it forms, this is my your zone. And it forms a stable complex carboxyhemoglobin, and hemoglobin remains very very busy with carbon monoxide. Carbon monoxide doesn't leave the hemoglobin. So hemoglobin, whose job is to carry oxygen to different parts of the body, doesn't do its job properly because it's not available. It's busy forming a stable complex with carbon monoxide, and hence what happens? Breathing difficult, sufficient oxygen doesn't reach the different parts of the body, and we suffer from various diseases, ultimately death also, right? If too much
Yes.
of if too much of oxygen sufficiency occurs, and the headache, this, that, etc., etc., finally can lead to, and no, plus 3 Fe is obtained. No, bad. I don't know. Write this APNOEA. I have no idea. Are you meaning anemia? Anemia, I've heard this one. I don't know. Something he has written which I don't know. Anyways, write it again, huh? Yes. So this was more of your bio things which you must be knowing better than me. Yes, even I have a good enough idea about this oxyhemoglobin being a much unstable complex. So once hemoglobin comes and you carries oxygen and supplies it to wherever it needs, it again gets back to its original form. Oxygen separates, hemoglobin again can go and carry remaining oxygen, but CO forms a very stable complex. So that's the problem. Fine. Anyways, so when steam is passed over coke, that also at such high temperature, what do you call it? Water gas. Any other name you know for water gas? It's given in the hydrogen chapter in NCERT.
Syngas.
Syngas.
Syngas comes from the word synthesis, because you can synthesize. Starting with this, you can prepare carbon monoxide. It can be used in the commercial method of preparation of hydrogen. Yes, syngas is a perfect term. Students, instead of steam, if you use air, you get producer gas, which is CO plus N2. Formic acid, you treat it or heat it with a dehydrating agent. Everyone knows H2SO4 concentrated is a dehydrating agent. So it will just remove water and you are left out with CO. Oxalic acid on dehydration using concentrated H2SO4 produces what? CO plus CO2 plus H2O. Very good. So carbon monoxide can be prepared with the above mentioned methods, as well as when insufficient amount of or limited amount of oxygen is available and coke or carbon is burnt, we get Carbon monoxide, very bad, very dangerous air pollutant. Correct, no students?
Yes, ma'am.
And suppose you are burning some coal or coke in a closed room.
Yes,
People
ma'am.
may even people may even die due to formation of a lot of carbon monoxide, and the oxygen content also uh, decreasing for that particular room. Fine.
Carbon monoxide and the oxygen.
Okay. So CO is neutral in nature. Students, in group 15, there are two other oxides of nitrogen which are neutral. I always correlate it like this. Which
Nitrogen.
are those? Which oxide of nitrogen? Because they are oxides of nitrogen. At least tell me the formula. That would be good
I know.
enough.
Nitric oxide.
Absolutely correct. One more.
N2O.
What a answering. I love it. Yes. So in the group 15 elements, N2O and NO as well are neutral, and our CO is neutral. Here we get to know. Yes, correct. You should know this. It burns with a blue flame. CO is neutral in nature. Poisonous, carboxyhemoglobin. You know the story. It can act as an oxidizing as well as a reducing agent. Students, do you know when that happens? What are the two extreme oxidation numbers for oxygen? Either I'm sorry, I used the wrong term. Oxygen, carbon. Carbon has four valence electrons. It can prefer losing all those four electrons, as in the case of CO2. Example, in CO2, carbon shows +4 oxidation state and loses all its electron. The other extreme is methane, where carbon shows -4 oxidation state. In CO, it has +2 oxidation state. So I'm sorry, it should write it closer to +4. So what do I mean is this. When carbon in CO has +2 oxidation state, it can either get oxidized and go to +4 state. It can gain and go to -4 state as well. So here, since it has an intermediate oxidation state, it can act as both oxidizing as well as reducing agent. Agreed?
Yes, ma'am.
And students, if you have any doubts, you can feel free to ask me anytime. You can interrupt me, no problem.
Yes,
I'll be
ma'am.
happy. Students, can you give me another example where the substance can act as both oxidizing as well as reducing agent? Number one, number two, only oxidizing agent, number three, only reducing agent. I'll write. Wait. First, like only oxidizing agent, the substance can act. A few examples, and only reducing agents. And then I would like to know the list where it can act as both oxidizing agent as well as reducing agent. Okay, I got an answer for this. K2Cr2O7. When the substance is present in its highest possible oxidation state, like in chromium, here is +6. Can't lose any more electrons. I'll add one more from my end. Wait, I should see the chats.
KMNO4.
Very good. I
KMNO4.
was going to I was going to mention KMNO4 only. KMNO4. In such cases, they can act as only oxidizing agent. The other extreme is when they cannot gain. So in the first case, in case of only oxidizing agent, they cannot lose any more electrons. They've lost all their valence electrons. Reducing agent, they cannot gain any more electrons. They have already gained whatever they could. They can't gain any more. And intermediate ones, HNO2,
Oxide. Hydrogen peroxide.
hydrogen peroxide. Excellent. So much you people are interacting. I was really scared. Suddenly I'll go and they will interact with me or not. Thank you so much. Yes, H2O is the biggest example because it undergoes disproportionation. It can get oxidized as well as reduced. So it can act as both. Perfect. Very good. So again, not deviating from the main point because redox is already over for you. Carbon monoxide due to similar reasons. can lose as well as gain electrons, can hence can act as oxidizing as well as reducing agent. Okay, it gets absorbed in ammoniacal cuprous chloride solution. This reminds me, students, um, there is a particular type of alkyne which will give a red precipitate with cuprous chloride solution.
Acetylene.
Any, not only acetylene, anything which contains an acidic terminal alkynes, right? Any
Yes,
terminal
ma'am.
alkynes, including acetylene. You are absolutely correct. Acetylene plus any terminal alkynes will give a red precipitate with ammoniacal cuprous chloride solution and white precipitate with Tollens
Tolerance reagent.
reagent. Fine, fine. Okay, if you want to estimate CO, treat it with I2O5. CO gets, it's an oxidizing agent. CO gets oxidized to CO2, and along with that I plus 5, right? I plus 5 gets gets reduced to I2. So I2 can be estimated. I mean, iodine can be estimated using sodium thiosulfate solution. Fine. Not a very important thing. Just you should know that when it reacts with I2O5, CO gets oxidized to CO2 and iodine is produced. Iodine can be estimated using sodium thiosulfate solution. I'm not going to into some n factors, though I'm very tempted to go to physical or organic because this inorganic is very much fact based. Coming back to the point, carbon dioxide, complete combustion of any of those hydrocarbons, methane, ethane, propane, acetylene, ethene, benzene. That's one. The other option is, say for example, okay, I have marble, CaCO3 plus dilute HCl. Fine. I get CaCl2, H2O, and CO2. Decomposition of CaCO3 that also liberates CO2. Many methods are there. Which is the alkali metal carbonate which can decompose, give liberating CO2 gas? Which is the only
Lithium. Lithium.
I have nothing to say other than appreciating you people are. Yes. Now your glucose in the presence of yeast undergoes fermentation and produces ethanol plus CO2. This first one to you already know. CO2 is a colorless, odorless gas, heavy, it's denser than air, with and shows brisk effervescence. You open the aerated drinks or soda bottle, you know, you have seen this. Students, this reminds me of a law in physical chemistry. Help me out. Read this. It's slightly soluble in water under ordinary pressure. But when you increase the pressure, with increase in pressure, the solubility increases at a given temperature.
Henry's law.
Very good. Very good. The Henry's law equation, mole fraction is a solubility, mole fraction of solubility, whatever you want to say. Tell me. Partial pressure. Partial pressure of
Is
the
equals to mole
of the
fraction
gas.
into total.
Yes. Partial pressure is directly proportional to the solubility, which is nothing but mole fraction only. P is equal to KHX, that Henry's law constant. Perfect. With increase in pressure, the solubility of CO2 increases. Henry's law, numericals, etc. You must be doing. Dry ice sublimes. Dry ice sublimes. That's the reason in movies and all, the the other day for Holi, I had like taken one more day leave also. I was watching some movie in some scene. They were just like that foggy thing, the cloudy thing. They do it with dry ice. Yes. It's weakly acidic in nature. CO2 is an acid NaOH is a base. It forms a salt Na2CO3. It is not a supporter of combustion. It dissolves in water and it's responsible for acid rain, no? Actually, small quantities of CO2 is always present in the environment, students. So, uh, rainwater's pH in general is, help me
Five
out.
to six.
Arre, wow, whatever you ask. I got that feedback from whatever you ask. Just ask. Yes, 5.6 is the pH of rainwater. It's not 7 because the normal air also contains some 0.03% of CO2, because of which a small amount of H2CO3 is produced. But the problem is not that. Due to a lot of air pollutants, what happens? No, you have a lot of CO2, SO2, NO2, and they all contribute to decrease the pH of this rainwater. The pH decreases. If it's less than 5.6, then it's known as acid rain. Anyways, H2CO3 splits in as H. It's a dibasic acid, no doubt. It's N factors 2. It splits as H plus and bicarbonates, which again splits as H plus and carbonate. So H2CO3, everyone knows, but I'm again writing your N factors 2, and you're a weak dibasic acid. N factor 2, weak. Degree of dissociation is less, quite less. Fire extinguisher, aerated drinks, Solvay's process. Anyone can at least tell me what is the purpose of Solvay's process, if not too many details?
To remove the permanent hardness of water.
Solvay's process, yes, produces dash, and that dash is used to remove permanent hardness.
CaOH taken twice.
Carbonate.
Does it prepare washing soda for us?
Yes, ma'am.
Yes. So washing soda is used to remove temporary hardness, but it's employed in the Solvay's process to prepare Na2CO3. And hydrated Na2CO3, I mean Na2CO3.NH2 is known as washing soda. And yes, washing soda removes temporary as well as permanent hardness. Good. Solid CO2 is used as a refrigerant. It's used to manufacture urea. By the way, urea, better we write as NH2CO, NH2, though they have given it like this. Silicon dioxide. See, SiO, SiO, SiO linkages. Can you see these linkages? Yes. It has extensive three-dimensional linkage or network. Supposed to be very hard, no? Yes. Can you predict the hybridization of silicon from this diagram? Sorry. sp3, perfect. Its silicon, I can see 1, 2, 3, 4, has shed all its 4 electrons to form 4 sigma bonds. Very good job. So crystalline form silica, amorphous form array. I'm not going to pronounce this name. God knows what it is. Yes. SiO2 is very inert due to absence of free electrons and a very strong SiO-Si linkage. But you will see that SiO2 reacts with NaOH as well as HF. When it reacts with NaOH, it forms Na2SiO3, sodium silicate. And students, this is also the formula of glass, no? Along with this, if you silica, glass, sodium silicate, it's present in sand, glass. Now glass. This reminds me, students, have you seen certain window pane design or in some glassware also? They do some designs. How do such a
Yes, ma'am.
strong glass and how do they do all those designs? They treat glass with HF, hydrofluoric acid. I want to ask one more simple question. HF or HI? Which is a stronger acid?
HI.
HI.
Why? You are correct. No doubt. There is no
Due
doubt.
to less overlapping.
Due to lack of yeah, and why that less overlapping? Lack of compatibility. Now this H is pretty small and iodine is this huge. So how can they effectively bond? Their orbitals will also, one will be very small, the other will be very large. Yes. So the bond is weak, lack of effective overlap. So the amount of H plus which it liberates is more in much more in HI than in HF. Sorry. So HF will react with silica to form SiF4 first, and then it will react further with SiF4 will further react with HF to produce hexafluorosilicic acid. And now using this acid, you can write write or draw, do whatever, or design, carve designs on this glass. Process is known as etching of glass, and it's important from the examination viewpoint. when Si2 reacts with HF, you will mention this as the answer. This one is important from the examination viewpoint. Fine. Carbides. Here I would like to know, without showing the slides and all. Carbides means carbon has a negative oxidation number. And what type of carbides do you know? Are formed carbides are formed when carbon reacts with some other elements.
Salt.
Be2C, Al4C3, Mg2C3, CaC2.
Silicon carbide.
Yes. So the first silicon carbide is one of them. Very good. So we have mentioned a lot of different type of carbides. The first type is when carbon will react or combine with metals like calcium or aluminium or magnesium. These carbides, yeah, I'll show you. These this should be registered here. Students, which carbide on hydrolysis produce methane gas? Which carbide on hydrolysis produces methane gas?
Aluminum
Beryllium.
carbide.
Aluminium as well as beryllium carbide. Which carbide on hydrolysis produces? This is the type of questions which will be asked. Knowledge is one thing, but you should know right now what are the pattern of questions. Yes, aluminium and beryllium carbides on hydro. I'll show you. On hydrolysis will produce methane gas. That's a question which is asked from carbides. And calcium carbide on hydrolysis produces
Acetylene.
Calcium.
ethane gas. ETH, C2H2. Ethine, very good. And magnesium carbide on hydrolysis produces produces magnesium carbide on hydrolysis produces. Suppose you get only this question, then propine gas. Wait. So there are three type of carbides. Carbides, one thing is very clear, carbon will have a -4 oxidation number. So you'll have ionic or salt like carbide, where the carbon will combine with metals of like a group 1, group 2, and group 3 metals. Methanides, they are the ones which produce methane on hydrolysis. Beryllium, aluminium. Important. This part is important. Look at the previous year questions, you'll realize. Methyl acetylene, yes, Karthik. Shefali, yes, you people are correct. But if I follow the IUPAC rules, I'll call it propine. CaC2 on hydrolysis will produce ethine. And Mg2C3 will produce C3H4, propine. Very important. Fine. So we'll just close our eyes and tell methane is obtained by the hydrolysis of Be2C and Al4C3. Calcium carbide on hydrolysis produces ethine. Magnesium carbide on hydrolysis produces propine. Okay, got it? Followed. And you remember this. Yes, someone was talking about silicon carbide. Silicon and carbon, they don't have so much of electronegativity difference. So boron and carbon or silicon and carbon, they will form covalent carbides. So when covalent bonds are formed, when the electronegativity difference between the atoms is not that much. Students, what is the electronegativity? The electronegativity should be difference should be greater than or equal to dash for a substance to form ionic compounds. Yes, by the propine, correct. Generally, what is given in the textbook? The electronegativity difference should be equal to or greater than dash for the substance to form. Yes, yes, high electronegativity. But what is that difference given in the books? Anyone remembers? Let me check. 1.7. The electronegativity difference should be equal to or greater than 1.7. Difference should be equal to or greater than 1.7. Then the substance is supposed to have like sufficiently strong ionic character. But you very well know Fajan's rule. Ionic compounds will have covalent character. You also know covalent compounds will have ionic character, by the way. So Covalent carbides are the ones which are formed when with the elements and the carbon, but the element and the carbon shouldn't differ much in electronegativity. So silicon carbon, they don't differ much in electronegativity. Boron carbon, they also don't differ much in electronegativity. Silicon carbide is extremely hard. You can see it's not just SiC, it's polymeric, extremely hard. Chemically inert, you can see such a compact arrangement, and thermally stable. So polymeric, extremely hard, chemically inert, and thermally stable. Yes. So carbides are ionic, covalent, and the third type, I can expect a metal lattice having some void, solid state over. So I can expect a metal lattice having some voids, and I can expect that in those voids, in those gaps, what is there? This carbide will be small carbide can accommodate itself. So interstitial carbide, the third type. So the transition metals will form a lattice. The metals in their lattice, in the interstitial lattice, oh sorry, voids have one other name, interstitious. In those voids or interstitials, so this orange one are transition metals arranged in a particular fashion. You know, so many fashions now: simple cubic lattice, body centered cubic lattice, face centered cubic lattice, right? So many arrangements, you know. So now what happens is in the gaps or the interstitials or the voids, what's there? Trapped carbon in the interstitial sites. They form which type of carbide? Interstitial carbide. Non-stoichiometric compound means if I find out the ratio of, suppose, just an example, I don't know this answer. This, or suppose there are 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6. 4, 6 are 24. 24 titanium atoms, and let me make one more. And 1, 2, 3, 4, 5. 5 carbon atoms. And 24 is to 5. Can be simplified. Will come out to be 4.8. So that's the reason it's not a whole number. For every one carbon atom, so for every 5 carbon atoms, if there are 24 titanium atoms, suppose. So for every one carbon atom, there will be 24 by 5. That's 4.8 titanium atoms. This 4.8 is not an integer. So it's known as non-stoichiometric compound. Now you have to help me out. As we move from left to right, actually we are going down the group: carbon, silicon, germanium, tin, lead. Here it's written left to right. So as we are officially, the correct one is as we go down the group, the thermal stability of the hydrides, think,
Increases down the group.
less stable, decreases. Why? You know, lead is too large, hydrogen is too small. They are not that compatible. While C and H, they are very much compatible. 2p 2p overlap. I'm sorry, 2p and 1s overlap. While the 6p and 1s overlap. So as we are moving down the group, the thermal stability of the hydride, that will be written here, decreases. And if I talk about what else, reducing nature. For a substance to act as a good reducing agent, it should be a good hydrogen supplier. Who can supply hydrogen best? Who can't be much compatible with hydrogen and is ready to, okay, you go, I'll supply you. So the PbH4. So as we move down the group, reducing nature increases. It says I'm not compatible, I'm ready to give. Thermal stability decreases, reducing nature increases. Why, Atika, you're sorry, you answered something else? I
Yes,
really
ma'am.
don't know why you're sorry. Okay, you can let me know. Sometimes I also miss out so many chats. Yes. So bond strength, of course, not compatible, decreases. Thermal stability, as I mentioned, it's it's not compatible. You heat it, it would separate easily. Reducing nature increases. It can supply hydrogens very easily or readily. Acidic nature, yes, PbH4 is ready to supply its hydrogen very easily. Increases. Anything else is there? Oh, this many. Fine. So, this. Can I ask a question then? Um, Particular alkali metal, which when heated in air, easy question, can form oxide as well as nitride.
Lithium.
Lithium.
Lithium, right? Lithium. Fine. A particular, okay, bicarbonates of which group are present in solution phase? Bicarbonates of which group elements, metals, chalo, are
Second.
present in? Very good. Okay. Do you know something about something very important here? Silicates and silicones. Fine. Now, tell me what are silicates and what is the smallest or the basic unit in silicates? SiO4 4 minus is the repeating unit. Yes. Before that, I would like to, it will come in the slides. I would like to draw and show SiO4 4 minus. You must be saying what is there to draw? SiU, right? O minus you put, O minus you put, O minus you put. Fine. I can put it this way. You'll understand also. Students, there is a typical way of writing these. When, just like Fisher, what is Fisher? You are forcing a 3D structure into 2D with certain rules. Exactly in the same way, the same thing will be written in a different way. For silicon atom, I will put a dot. Sorry. Yes, for silicon atom, I'll put a dot. Yeah, the inorganic, not organ, in inorganic. Organic, there are wedge dash, Fisher, Newman, Sawhorse. Out of that, in Fisher projection formula, we force something which is in 3D to be projected as 2D like this. It's actually a 3D molecule. These two are actually above or below the plane. Organic is my favorite. I will deviate otherwise. Bring me back. These two are actually vertical positions are actually those groups which are present very good below the plane. Horizontal ones which are represented by cross. These four are actually above the plane. Vertical, yes, so many answers. Very good. Below the vertical, below the plane. Horizontal, above the plane. Good. But that's in Fisher. Here we are talking about inorganic chemistry. Here the rule is very simple, very one simple rule. Silicon will be represented as a dot. And you have four oxygens, I mean sorry, O minus bonded to it. O, you can put a minus, minus, O minus, O minus. The fourth oxygen is actually in a plane, I mean sorry, the fourth O minus is actually in a plane above silicon. But how will you represent it? I'll put it here, O minus, indicating that this O minus is not present on the top of silicon sitting and dancing. It's present on a plane above, but in 2D on a paper, on a screen, what should you do? You will put an O minus, indicating that this O minus is just above this dot. This O minus is just above this dot. So this dotted line is not like a bond. Just to give you a triangle like feeling. If you are getting confused, you will not draw this dot. In case you're getting confused. Otherwise, I'll repeat this thing once again. I feel I should repeat this once again before beginning silicate. So SiO4 minus can be represented in a 2D plane in a little bit different way, where silicon atom is represented by the dot, and this dot is bonded to O minus, O minus, went little this way, O minus, and the fourth one O minus on top of silicon on a plane above will be represented like this. And I always draw this. I feel it is incomplete without this, but it is not a bond. Just to give you a triangle like feeling, just to give you a feeling that the three oxygens are present at three corners of a triangle. That's the reason these dotted lines, nothing else. Silicon and oxygen atoms have poor tendency to form pi bond. Why is it so? Oxygen can form a stable pi bond. No, why? Why so much of problem here? Why is it creating so much of trouble here? Because pi is formed by sideways overlap. Anyone can answer this? Why a silicon or an oxygen silicon pi bond will not be very stable? Because pi is a very weak bond. Sideways overlap. For sideways overlap, no, you can't bring very big orbitals. Say, for example, I think of two lean people coming closer and forming this kind of sideways bond. But think of back bonding, 2p 2p. One lean person, the other fat one, chalo, I will somehow manage. Suppose this is 3p. Two fat people, nah. No, no, no. Very difficult. The extent of this overlap, no, though I've shown it quite big here, I should erase it, will be very, very less. That's the reason pi bond involves sideways overlap. 2p 2p small can come closer. To certain extent, you can have good overlap. At least one of them is 2p and the other 3p. Okay, accept it. To some extent, like 2p here and 3p here. To some extent, yes. Some extent, not very strong. It will happen, not very strong. So it will have a poor tendency to form 5 bond. So what do they do? No back bonding from oxygen to silicon. No. So silicon and oxygen atoms will have a poor tendency to form pi bond due to lack of effectiveness of overlap. So these silicates ion have a tendency to form polymer. It forms single bonds and forms polymers. How is it? Let's have a look. This is a basic structural unit. This is silicic acid. Remove both all the 4H plus from this. You get SiO4 4 minus. Correct? No doubt it's sp3 hybridized. Did you understand this dot? O minus, O minus, O minus. See, now this dotted line gives you a proper feeling. And this O minus is on the top of the silicon. This O minus is on the top of this silicon. Got my point? Understood, right?
Yes, ma'am.
Yes. But this is the most simple of the basic silicate. And what is its name? O for
Orthosilicic acid.
ortho, O for organic. Yes. It's orthosilicate. Orthosilicate is what I just now discussed. There's a single unit. No oxygen atom is shared. Nothing. General formula SiO4 4 minus. Zircon. Zr. Zirconium is plus 4. SiO4 is 4 minus. Simple. Orthosilicate. Try to remember all of them. One or two questions after this I have asked. Pyrosilicate. Now see. Very nice animations to explain you. This is one unit. This is another unit. How will you join them? For joining them, for combining them. One oxygen atom will be common to both the units. Okay. So this is the oxygen, which is common to both the units. So it will not carry a negative charge. When you have something as O minus, when it's present alone in a corner, when this oxygen will be bonded to something else on both the sides. So this has three lone pairs and extra negative charge. But when it's bonded, valency is 2, no. O minus is like this. If it's bonded on both the sides, then it will not have, then this will not have a negative charge. Have a look once again. They have removed it already. This should be minus, this should be minus. But since it gets combined or joined like this, the oxygen will be neutral. It will not have any charge. Can you count how many silicons and oxygens are there and how many charges? Si 2. Oxygen 1, 2, 3, 4, 5, 6, 7. And how many negative charges? 1, 2, 3, 4, 5, 6. This will not have any charge. Neutralizes. Si2O7 6 minus is the anion which is present in pyrosilicate. First one is orthosilicate, SiO4 4 minus. Why am I repeating this? Because when I repeat, it gets registered in your minds there when you're listening. Pyrosilicate, Si2O7 6 minus. Two basic units. One oxygen atom shared between two units. Si2O7 6 minus. Si2O7 is there. Hemimorphite. This name I don't remember that much. But yes, from that formula, you should be able to identify. Yeah, it's a pyrosilicate. What's the next type? Single chain silicate. In case you're wondering what and all is there in this session, silicones and silicates. That's it. Silicates almost we are doing, and then silicones. And then all the important points in group 14 will be covered. Anything, anytime. Students, you don't have my number, no? I've never shared. Neither I'm in your group or something. Can feel free to ask me. Yeah. Now I've written it on the screen. You can feel free to ask me in case you have any doubts. SB, my initials, yes. Single chain silicates, one unit. Here, prepare a chain with beads, right? Follow the same logic. What logic? 1, 2, 3, 4. Now, one thing doesn't come to your mind. Why is it like up, down, up, down? Why not this pattern? Girls, you'll be very much interested now when I'm coming to all these, huh? This is also single chain, doesn't matter. This or this doesn't matter. This like more neat. Otherwise, in our designs, we may find a difference, but here or here, practically doesn't matter if you write it up or down in chemistry, chemistry wise, chemically. Huh? Maybe looks more neat, the chain like this. You can go by either ways, not a problem. But I would like to ask you one thing. Which is the repeating unit in it? What do you think? Students, this I put a minus in case it's the starting one. In case it's the ending one, there will be a minus. If it continues, it will not have any charge. Suppose, imagine there's not a unlimited space here. This is the first one, this is the last one. Except the corner ones. How many oxygen atoms per unit are shared? Except the corner ones. Except the corner ones. I repeat, except the corner ones. How many oxygens per unit is shared?
3.
Two.
4.
Two, two, two. Look at this. Look at this. Except the corner ones. Corner ones will share only one. The corner one is sharing not this, not this, not this, only this. corner one is sharing one, otherwise only two. This is not being shared, this is not being shared, only two. Have a look again, think. Corner one, only one it is sharing. The one at the center other than the corner, they're sharing two oxygens here. This is shared and this is shared. For the corner, only this one is shared. Agreed? So it is a chain 20, 30, 40, 50, 5,000, 6,000, 7,000. Let it continue. So n number of units are there. General form, I should wait. Yes. Now you have to tell me which is so two oxygens are shared in all the cases except the corner atoms, which shares only one oxygen atom. Now, now you have to think about the repeating unit there. Repeating unit, which is being repeated again and again, except the corners. Leave the corner. That's an extreme case. Look, have a look at this. Up or down doesn't matter. This part is being repeated. There is an oxygen which is common to both the rings, and then dot O minus and a O minus. This one or this one, same thing. This one or this one or this one. This up or down. This pattern is being repeated. You can see four cases I've shown, except the corner ones. And hence, the repeating unit is, I've shown four. You can take any one. SiO3.
2 minus.
Very good. SiO3 2 minus is the repeating unit. Up down, as I told, doesn't matter. They have, for more neatness, not they have not written it like this. They have written like this. Basically the same thing. So SiO3 2 minus is the repeating unit in single chain silicate. SiO3 2 minus. This is one unit. How many such units are there? This is one unit and this is a repeating unit. N such units are there. Forget the extremes. Now, central unit, except the corners, two oxygens are shared. Corners, only one oxygen is shared. Terminal is corner. Other than that, other than corners, they are the central units. You can just call it. Two oxygens are shared. And then you can go with this. These examples, why did they keep 10 and not 9? SiO3. Wait, I'll check this. If it's Si3O9, I'll check. Meanwhile, you tell me any doubt you have or not. Ca plus 4. Mm, silicon is plus 4 plus 12. And I'll check this. Is it because otherwise the substance will not be neutral? I'll have a look. I'll check this once. Yes. See, yes, Faizan. Perfect. Yes. Cu2O is there. And Si3O9 is there. Cu2O. And in that way, yes. Otherwise, the thing will not be neutral. But still, once I would like to check. Yes. Next. Cyclic silicate. See, chains are there. I said down or up doesn't matter. I've already told. Down or up doesn't matter. Same thing. This is also single chain silicate. Wow, how nicely it forms a ring. So students, in cyclic silicate, there's no case of no end one different, center one different, everything is same. What's the repeating unit here? Tell me. The same thing is taken and now a ring is formed. So the repeating unit in the previous case and here should be the same.
SiO2.
It should be the same. The same thing is taken. The same thing is taken. This is the question. Yeah, there's only a difference here that the end part and the center parts, the shared oxygens, etc., is not the same. The scenario is not the same. But if you are making it still simple, same thing, same thing again. So the repeating unit will be the same. Every unit has two oxygens shared. Agreed?
Yes, ma'am.
Ma'am.
Yes. And general formula is the same without any differentiation for the end part and all. Yes. So cyclic silicate and single chain silicate SiO3 2 minus is the repeating unit. Si2O7 6 minus pyrosilicate, SiO4 4 minus orthosilicate, sheet silicate. Now see, one chain, one more chain, one more chain, one more they have shown or not? Ah, one more. There was space, they put one more. So how many chains? One, two, three, four. And in that way, unlimited single chain silicates. Go on adding it. Forms a sheet silicate. Here you help me out. What will be the repeating unit? I know it's little smaller in size. What's a repeating unit? Leave the end ones. End ones behave differently. See the center one and find out the repeating unit. A particular thing is being repeated. This one, this one, this one, this two. You see in all cases. You will definitely agree. You take this side or this side doesn't matter. This part is being repeated and it is Si2.
Oh,
1, 2, 3, 4, 5. But minus only 2. This is being repeated. Repeating unit is very important. How many oxygen atoms are shared? Tell me. Center part, how many oxygens are shared per unit? Per SiO4 4 minus unit? 1, 2, 3, no? In sheet silicate, 3 oxygens are shared by the center units. Yes. This is very important. 3 oxygens are shared by the center unit per unit. General formula is also correct. This is one unit, repeating unit, and there are n such units. Yes. The last one. Three-dimensional sheet silicate. Now you have to imagine this. The last one can only be imagined. This you can you see multiple chains when joined together forms a sheet. Now you place. Imagine it's a 3D. See my hand. You place this one sheet. You place another sheet here, another here, another here. Keep on placing sheets one above the other. It forms a. You can't do it here or show it here. One sheet, no. It consists of multiple single chains. Second sheet, third sheet, fourth sheet, and so on. Forms a three-dimensional silicate where all the four oxygens are shared, and this is the only way to represent it. The general formula is also SiO2 whole N. Yes, 3D sheet. All the four oxygens are shared, difficult to be practically shown. Hence, yeah, you just know all in the center, all the four oxygens are shared. SiO2 whole N is the repeating unit. Hence the general formula example is silica. Students, have you heard of zeolites? Because you've studied surface chemistry and everything, right? Zeolites are a type of silicates, aluminosilicates. It belongs
yes.
to which type? Ortho, pyro, single chain, cyclic, sheet, three-dimensional. They will ask you. By the way, answer this meanwhile. Name the type of structure of silicate in one oxygen atom is shared. Which one? Yes. Others? You can say it aloud.
Orthosilicate.
No. In orthosilicate, no oxygen is shared. Shared. Now is it clear? It's confusing, maybe. If no oxygen atom is shared, orthosilicate. One oxygen atom is shared,
Pyro.
pyrosilicate. Yes. Answer this.
Pyrosilicate.
Yeah, pyrosilicate for this question. Agreed. Done. What about this? Cyclic silicate, I've asked. Option?
Four.
What
Very
option?
good. So can I write here? This is for orthosilicate. This is for pyrosilicate. This is for cyclic and this is for
2D sheet.
very good. That's it. Done. Here the answer is 4. Zeolite is sodium aluminum silicate. Zeolite is a three-dimensional silicate. You should know this. It's used to convert or make hard water soft. Permutate zeolite Na2Z plus hardness causing ion Ca2 plus will be there. Caz will be formed and 2Na plus will be liberated. The Ca2 plus is a hardness causing ion, it will be precipitated, etc. etc. Yes. Now, students, you should also know that ZSM5 is a type of zeolite. It's given in NCERT. It converts ethyl alcohol into petrol. Glass and cement are man-made silicates. Certain facts, certain things which they can ask from NCERT. Now, silicones. Students, silicones, first of all, can you tell me what are silanes? SiH4. Silane. Next, chlorosilane. When the hydrogens, one or more hydrogens are replaced by chlorine. SiCl4, I'll call it chlorosilane. Silane, what I'm telling, I'll tell you. Chlorosilane, again, this is important. Last 5-10 minutes, have patience. Exam wise, silicates and silicones are important. Chlorosilane. Now, if I replace 3 of them with the alkyl group or 2 of them with alkyl group or 1 of them with an alkyl group, they all will be categorized as alkyl chlorosilanes. Yes. So silicones are organosilicon polymers containing R2SiO linkage. I'll show you. They are very chemically inert. They have polymeric structure, and due to water repelling nature, they can be used as like in the raincoats and all that kind of material. Because of its water repelling nature, polymeric nature. Insulators, waterproofing ability because of the absence of free electrons. I'll discuss all those. But you have to know silane, chlorosilane, one or more chlorines are replaced by alkyl groups. 3, 2, 1. R4Si is of no importance to us here. So they are known as alkyl chlorosilanes. Now what happens is this. Take which one? R3SiCl. Hmm. As I was telling, alkyl chlorosilane, and I'll show you. I'll explain this properly. Huh. So what we do is we take R3. One second. Just a minute. Huh. We take R3SiCl. Students, when you hydrolyze it, what will happen? Water will attack. Cl is a good leaving group and it will go off. OH will be. OH is a stronger nucleophile. Stronger will come, weaker will leave. Weak bases are good leaving groups. R3SiOH will be formed. I've taken R3SiCl. Hydrolyze it. It will become R3SiOH. Take this one. Take this one. What will happen, you know?
Dehydration.
Ha. But what happens? No, there are this much. Nothing else we can do. We can just form a dimer. This polymer, what I was saying, polymer silicones, polymer can't be formed here. So have a look. R3SiCl on hydrolysis gives R3SiOH. So one more R3SiOH will combine with it. OH and H are lost here. Okay. R3Si, O R3Si. So it's called as chain terminating silicon because one dimer you get and the reaction stops. Can't do anything more with that. Forms a dimer. Done. But I have a lot of space. I'll show you something else also here. But in case if it is R2SiCl2, this on hydrolysis will produce R2SiOH whole 2. What will it produce? R2SiOH whole 2. One I wrote. Second one I wrote. Third one I wrote. And so on. So now what will happen is they will bond. OH of this, H of this. This will say CH I gave, no OH you have to give. If H is gone, your OH and so on. If OH is gone, your H with someone else. And what will be formed? Will it form a polymer? Which kind of polymer can I call it? A straight chain?
Linear chain.
Linear chain, straight chain. Very good. Just a minute. 1 second, students. Yes. R2SiO. Si and so on. Linear chain silicates are formed. Let's have a look. R2ClCl will become R2OHOH and will go on losing water and form linear chain silicon. And this is the repeating unit R2SiO. So R2SiO is the repeating unit. I can put an N here. Now, last. Once again, 3:30 we'll meet after the lunch. Yes. Cross-linked silicon. Suppose I have RSiCl3. We'll give you RSiOH whole thrice. Then you can remove water linearly and sideways also. I'll show you here. Do we have a blank slide or something like this? Acha, chalo, here. Here I can show you R, OH, OH, OH. Sorry. SiROH. One unit. One more here. Wait. 1 second. 1 second. Lack of space. What happened there? 1 second. Okay. R SiOH. One second. Can you see the screen?
No, ma'am.
No. Okay, fine. No problem. What I wanted to show is, I'm so sorry. OH. And I'll have one more. Ah. Think of this. Think of one more like this. One more. This 4 will do. Here it will lose a water. Here it will lose a water. As well as here it will lose a water. Here it will lose a water. This side it will lose. This side it will lose. So ultimately what I get is
Cross-linked.
cross-linked. So it will be like this. R, S, I, O. This also with someone. This also with someone. R, S, I, O, O, O. S, I, R, O. S, I, O, S, I. Here S, I, O, S, I. Like this. So ultimately I get a cross-linked silicone. Yes. Fine. We'll again meet at 3:30. Maybe I can ask you a few questions on group 13 and 14 and we can start group 15. Bye bye students then. I'll upload this. The meeting will automatically end now. Okay then. Bye. Thank you. Thank you. We'll again meet at 3:30. Yeah. Don't forget that. Have your you have a lunch or do you have one more class also in between, right?
At 3:30, yeah.
Okay. So quickly have your lunch now and then again join the next session. Bye.
Bye.
Bye everyone.